Let me begin with a real incident from an electrical installation. A delta star transformer was in service with the star side neutral grounded through a low resistance grounding resistor NGR. The transformer was equipped with the differential protection, the well-known 87 scheme. One day, the phase to earth fault developed in the low voltage star winding. It was expected the differential relay will act immediately, but it did not. The fault persisted, the NGR overheated, and it failed. Eventually, the neutral became effectively solidly grounded, and only then did the differential relay operate. By that time, the transformer had already experienced stress and the NGR was damaged. This incident raises an important question. Why did not the differential protection act right away? After all, isn't differential relay supposed to cover internal faults? Similar events have occurred at other sites, and every time engineers ask the same questions. Why did differential protection miss to detect internal fault? And what else could have been done to detect it sooner? In this video, we will find answer to these questions. To understand this, we need to revisit how fault currents behave in a delta star transformer. Let us consider a single phase arrangement. Imagine an earth fault occurs at the winding terminal. The voltage behind the fault is Vs, and hence the star side current will be Vs upon R, where R is the NGR ohmic value. This is the maximum earth fault current in the star wind. To find the delta side current, we can apply ampere turn balance, and hence the delta side current will be turns ratio multiplied by Vs upon R. And this is the maximum delta side current for an earth fault on the star winding. Now imagine that instead of a terminal fault, an earth fault occurs somewhere in the middle of the winding. The voltage behind the fault is X times Vs, where X represents the fault point from the neutral. The value of X will be 0 for a fault at the neutral and 1 for a fault at the terminal. So in this case, star side current will be X times Vs upon R. Again, to find the delta side current, we can apply ampere turn balance. Here is an important point to note. The effective turns on the star side will be X times Ns, not Ns. So the delta side current will be X square times turns ratio multiplied by Vs upon R. From these equations, we can observe that when an earth fault occurs on the star winding, the current on the star side varies proportional to the distance from the neutral. However, the current on the delta side does not varies linearly. It increases with the square of the distance from the neutral. This relationship is key to understanding why the differential relay fails to operate for most faults occurring on the star wind. To understand it in detail, let us consider a specific example. Take a 25 MVA 33 by 11.5 kV transformer. This transformer is equipped with a differential protection. The delta side CT ratio is 500 by 1 ampere and star side CT ratio is 1300 by 1 ampere. Transformer star winding neutral is grounded through a low resistance value of 13.28 ohm so that the star side earth fault current is limited to 500 ampere and hence the corresponding delta side current will be 100.6 ampere. The minimum differential current pickup setting is set at 10% and hence at least 50 ampere of current on the delta side is required for the 87 element to operate. For this specific example, let us see how the delta side current and star side current varies with respect to fault current position. In this table, we have calculated the star side current as well as the delta side current with respect to the location of the fault from the neutral point. We can see that up to 70% of the winding, the delta side current is less than 50 ampere and hence the differential relay 87 will not pick up. It will pick up only after this point. Let us see this in the circuit drawing. What does it? From the neutral point up to 70% of the winding, if any earth fault occurs, the delta side current will be less than 50 ampere and hence the differential relay will not pick up. So only 30% of the winding is protected by the differential relay. So the question arises, what is the solution for this kind of problem? The solution to this kind of problem is providing restricted earth fault protection. The REF protection does not rely on the phase currents alone. Instead, it compares the vector sum of the phase CTs with the neutral CT. If there is any imbalance between the vector sum of the phase CTs and neutral CTs, the REF relay will pick up and hence it will protect the transformer for the earth fault in the low voltage winding. To understand REF operation clearly, let us look at the three conditions. First, we will start with the normal load condition. Imagine this transformer is feeding power supply to a three-phase balanced load, and these white arrows represent the load current flowing through the transformer winding. The current through the phase CTs will be balanced and 120-degree apart, so the vector sum will be 0. Since there is no earth fault currents, and hence there is no current through the neutral CT. Therefore, there is no imbalance current which can flow through the REF protection relay. Now imagine internal earth fault occurs in the LV winding of the transformer. Under this condition, these white arrows shows the current flowing through the transformer winding, and the red arrows represents the current flowing through the protection circuit. We can see that there is no current through the phase CTs, but there is current through the neutral CT. And this imbalance current will flow through the REF relay. If this imbalance is more than the pickup value, the REF relay will pick up and it will trip the breaker. Consider an external fault which is outside the protection zone. Under this condition, we can see that there is current through the phase CT and there is also current through the neutral CT, and these two currents are same. Therefore, there will be no imbalance current which can flow through the REF relay, and hence REF relay will be stable for external fault. So we have seen that the REF relay can reliably detect the earth fault current on the LV winding. It is stable for any external fault and it will operate only for the internal fault. The key takeaway is this: differential protection is excellent, but it is not enough on its own. It cannot detect all earth faults, especially those on the LV winding of the transformer. REF fills this gap, ensuring that the entire winding is covered. For critical and expensive assets like power transformers, relying on differential relay only is risky. Combining it with REF protection ensures complete, fast, and sensitive fault detection. In short, if we want dependable transformer protection, REF is not optional, it is necessary protection.